Hello everyone, this is one more problem from Halliday Resnick worker, problem number 29. In this problem, it said that there is a conducting rod which has a radius r and it has some charge q1, and around that rod there is a conducting spherical shell which has a radius r2 and charge is q2. This charge q2 basically the minus 2q1 and q1 actually the plus 3.4 into 10 to the minus 12 coulomb. Now we have to find out that magnitude and the direction of the electric field at different distance. The first one is say that when that r equal to 2r2, in that point we have to find out the electric field. In the second case we have to find out the electric field and the direction when r equal to 5r1, and last one we have to also find out what is the charge in the interior and exterior surface of the shell. So we have to find out that one. We can find to solve this question, basically we are going to use the Gauss's law, and the Gauss's law is tell us say that finite any enclosed surface would be E dot dA must be equal to Q enclosed divided by epsilon naught, right? So this is actually that Gauss's law, we know that one. Fine. Now over here they give us some parameter actually. So R1 actually 13 millimeter, so I'm writing that one. R1 actually 1.3 millimeter. That's I'm going to convert that actually in meter. It should be 1.3 into 10 to the minus 3 meter, right? That's how actually we can convert this thing. And that R2 is basically 10 R1, which is it would be 13 millimeter. That's we can also write down 13 into 10 to the minus 3 meter. This is the radius of that one. Fine. To find out that first one, to find out that electric field, first I have to choose a Gaussian surface. Say this is actually that perspective view of this one. Say I'm going to say this is actually that rod which has a radius, say that r1, and this will be the charge q1. This is that the radius, so r2, and the charge, the total charge over there is a q2. That's given. Now in the first case they say that when r we will choose a Gaussian surface whose radius in the case r actually 2r2, that should be basically 2 into 13 into 10 to the minus 3 meter. It means that my Gaussian surface must be outside of that spherical shell, right? So I'm going to draw a Gaussian surface by using the different color. Say this is actually my closed Gaussian surface. I'm choosing, say, for that case number 1. Say it's a closed Gaussian surface, and into that Gaussian surface, say the radius of that Gaussian surface is small r. Now I'll choose at any point, say at that point I'm choosing, say that the electric field direction is that direction. I draw electric field vector, and also the area vector would be towards that direction. I draw arbitrarily, I don't know which direction would be that one electric field. Fine. Then To find out that electric field, I'm going to use Gauss's law. So what would that? I'll write, say that enclosed E dot dA must be actually that Q enclosed divided by epsilon naught. Now this my Gaussian surface now going to enclose the total charge, which is the charge inside that cylinder and also the charge inside the total charge of that shell. So that's mean my enclosed charge for this case would be Q1 plus Q2 divided by epsilon naught. See, in my closed Gaussian surface actually outside of the shell, it going to the enclosed the charge inside the cylinder and charge inside that spherical shell. Fine. Then what I can do, I know these two vectors are parallel to each other, so angle between them is 0 over here. I'm choosing, so then I'll find out that dA is going to be Q1 plus Q2 divided by epsilon naught. Then this I have to integrate that one. So if I integrate this dA, I'll find out that area, right? So what would be that? Q1 plus Q2 divided by epsilon naught. And what would be that? If you integrate, you will find out that E is going to be A equal Q1 plus Q2 divided by epsilon naught, or this area, I have to find out that area of that cylindrical shape, right? You have that idea how I'm going to find out the area of the cylindrical shape. So this is the radius of that cylinder, and this is actually say that height or the length. Then the area of this cylindrical shape is twice pi r into L, right? So that should be the total area of this cylindrical shape. So that's why I'll write down it should be twice pi r into L must be equal to Q1 plus Q2 divided by epsilon naught, right? So because the length of that cylinder and length of that spherical shell are equal, so that's why we can write down the area of these two systems will be twice by r into L. Now what I'm going to find, so it's the Q1 plus Q2 divided by twice pi into epsilon naught into r into L. So that is would be that magnitude of this electric field at any point of r. Now for the first case, they give me r actually that twice r1, right, which is for this case, sorry, twice r2, I'm sorry, it should be that twice r2. So if it is twice r1 for the case, right, so this is actually that twice r2, which is actually that 22 into 3 into 10 to the minus 3 meter. That would be that r. Fine. Now I'm going to put that value. What would be that? Is going to be Q1 is basically 3.4 into 10 to the minus 12, and Q2 is that given Q2 is basically minus 2Q1, right? So Q2 is basically minus 2Q1. They need to be minus 6.8 into 10 to the minus 12 divided by twice pi into 8.85 into 10 to the minus 12 is epsilon naught. R is 2 into 13 into 10 to the minus 3 into L is 11 meter is given into that quotient L, actually that 11 meter. Look at this, they given the length of this is 11 meter over here. Fine. So if you solve, you'll find out that strength of this electric field, you'll find out it will be minus 0.214 Newton per Coulomb. So this is that magnitude of this electric field, and this negative sign actually they're telling us that electric field strength would be towards in that inward. I choose that is the outward, but since I find out that the is negative, is going to be basically inward. So this is the direction of that electric field over here. So then this is the answer of that question number A, who is asked you that magnitude and the direction. So if you say that the magnitude, so that magnitude E is 0.214 Newton per Coulomb, this is that magnitude, and the direction would be inward. So this is that answer number B. So this is that question number answer of the B. Fine. Now in the C, they ask you, C and the D, what would be the direction and the magnitude of the electric field if the Gaussian surface are equal to 5r1. So this is the case for C, electric field. Say this is fine. Say for this case, this is my R1, this is that Q1, this is actually that R2, and this is actually that Q2. Now my Gaussian surface for this case R would be basically that 5R1, right? For the case 5R1, so R1 actually that 1.3 millimeter, right? So if I do that, then 5 into 1.3 into 10 to the minus 3 meter, that's going to be, it would be, in that case this is going to be 1.3 into 5, 1.3 into 5 is going to be 6.5, 6.5 into 10 to the minus 3 meter, which is actually that less than of R2, right? Because R2 is basically 26, sorry, R2 is basically 13 meter, 13 sorry, 13 into 10 to the minus 3 meter, whereas this Gaussian surface would be 6.5 into 10 to the minus 3 meter. That means 6.5 millimeter. In that case, my this new Gaussian surface would be inside that shell but outside of that cylinder. It means that this Gaussian surface is going to enclose the charge only that Q1, right? So this is, say, that Gaussian surface. Say this is my R. This Gaussian, new Gaussian surface is going to enclose only the charge Q1. It means that that charge inside that cylinder. Okay, fine. Then we can use the same formula, which is actually that we derive over here. I'm going to write over there. Now that enclosed charge would be Q1. Then I will be able to write this would be E1 divided by twice by R into L into epsilon naught. So this would be your formula to find out. Now if you plug in that value into that equation, what you will find? You will find out this thing would be, I'm sorry, I write it E1, it would be basically Q1 is going to be Q1. So that Q1 is going to be 3.14 into 10 to the minus 12 into twice pi into R is 6.5 millimeter. So 6.5 into 10 to the minus 3 into L is 11 into epsilon naught would be 8.85 into 10 to the minus 12. If you solve this one, you will find out that E would be positive 0.790 Newton per Coulomb. Since that E is positive, definitely the direction of that electric field would be basically is outward. So this would be the direction of that electric field for this case. So that's why your answer of the C would be the magnitude of that electric field is going to be the 0.790 Newton per Coulomb, and that answer of the D, it would be outward. The direction of this electric field at R equal to 5 R1 would be radially outward. Fine. Now what about that E and F? What is the charge on that interior and exterior surface of the shell? Fine. To find out that exterior surface and interior surface, I'm choosing, say, this is my Q1 is say R1, and so this is actually that Q2 is the total charge into this shell, right? So, and this is actually that R2. Now I'm choosing, say, that the inside of that shell is that total charge is Q in, and outside of the shell is would be that Q out. This is actually that case. Now since it's a conducting shell, then the total charge into that shell must be actually that 0, right? It's written over here. Look at this. This is actually that conducting cylindrical shell and conducting rod. So that's why the total charge into that would be basically actually into that surface. So that's why total charge is going to be that 0. Then I can write, say, for the case of that, when I choose that this Gaussian surface, say that at the inner surface of that shell, right, then there will be no charge over here. We know that for conducting shell, all the charge will be basically outside. So that's why this Gaussian surface enclosed charge would be basically that, although its enclosing charge is Q1, Q inner plus Q1, that must be going to be the 0, since conducting surface, both the cylinder and spherical shell is conducting surface, there will be no charge for the shell in the inner surface. It would be basically the total charge would be basically outer surface. So that's why, since I choose that Gaussian surface, actually that inner surface, which is enclosed the charge Q inner, and that Q1, which is charged at the outer surface of that cylinder, that must be going to the 0. It means that my Q in must be equal to minus Q1, which I can say that it will be the minus 3.4 into 10 to the power minus 12 Coulomb. So this would be actually that charge in the inner surface of that shell. And what about that outer surface? For the outer surface, We know that when you choose that Gaussian surface, say that at the boundary of the outer surface of that shell, then is going to be the enclosed charge would be basically Q outer plus Q inner, which would be basically the total charge of that outer surface of that conducting shell, actually that Q2, right? This must be actually that whatever the charge inner and outer must be actually the Q2, which is the total charge of that conducting shell. Then we can write, say that Q outer surface would be Q2 minus Q in, which is actually that Q2 minus is going to be that Q in is basically is plus Q1, right? Because Q in basically that minus Q1. Now Q out, we can find that Q2 is basically minus 2 Q1 plus Q1, right? Q2 actually is given, Q2 actually minus 2 Q1, that is given over here. So Q2 is basically the minus 2 Q1. In that case, you will find out that Q out, the charge on the outer surface of this spherical shell would be minus Q1, which is basically minus 3.4 into 10 to the minus 12 coulomb. So that is would be actually that charge on the outer surface of that conducting shell. So this is the answer of that case. So that's when inner and outer surface is the same charge. That's why the total charge on that shell is actually that twice Q1. Okay, thank you very much.